Hi, my name is Brandon Graisley. I'm a high school math teacher. We're going to learn about extrapolating periodic functions. Extrapolating means to extend the information that you have to predict beyond that information. And for periodic functions, that means to calculate the function's value usually for an x value that's past what you already have. So we're going to look at a specific example here, and I'm going to give you a strategy to use whenever you're trying to extrapolate. So we have this function f of x. It has a domain of all real numbers starting at 2 and going up from there. So there's the beginning of the function, and it continues forever in this direction. So maybe just put an arrow there. The range is between -2 and +1, so you can kind of see that right here. And so let's find the period first by trying to identify a cycle. Looks like it kind of has this curvy upward part and a straight down part, curvy upwards, straight down. And so one cycle is right here, and then there's another cycle, and we have almost 3 cycles shown here. So I'm going to start by identifying the beginning and end of a cycle just by putting a little box around it. That's easy to see. So there's one cycle, and this is at 6, an x value of 6, and this is at an x value of 2. And so the period is, I'll take this higher x value 6 and subtract the lower x value 2 to find out that the period is 4. That's how wide each one of these is. And so our next question is, what is the x value of the next peak that is to the right? So the peaks are these maximum spots. So there's one there. We already know that's at 12. This one's at 8. And this one's at 4. And you can see the pattern that develops here. 4, 8, 12. Now, to find out the next peak, we take this peak here and we add on the period. So the next peak is at x equals 12, the given number, plus the period. This is the peak we know. This is one period away where exactly the same thing happens to the function. So that'll be at 16. Similar question, what is the x value of the next trough to the right? Troughs are the bottom parts where it hits a minimum, and there's only one per period here, so that works out nicely. So when is the next trough? The next trough is at x equals, well, let's look at our last trough. It's at 10. Add on the period, 4, and we get 14. Maybe I'll just label both of those here. That is the period that we're adding on. So that's the key idea, is that you shift over by some number of periods, in this case just 1 to find the next trough or the next peak, and from a reference point that you already have. Okay, let's get into some more challenging questions. What is the value of the function, the y-value, when x equals 19? So we're going to go back to our graph and take a look at that. Well, we have a pattern of trough, peak, trough, peak, trough, peak, and those happen 2, 4, 6, 8, 10, 12, and so on. So we're trying to find out what happens when we get to 19. So we can just follow this pattern, 4, 8, 12, the next peak would be at 16, and the next peak would be at 20. So following the pattern of peaks, we can find out that we'll have a peak at 20. We could also follow the pattern of troughs. 2, 6, 4 more is 10, 14, 18 is a trough. So let me just write that down here. Following our pattern, troughs occur at 2, 6, 10, 14, 18, and I'm going to put a little ellipses at the end there that says that this continues on, and those are troughs. So peaks occur at, we started at 4, then 8, 12, 16, 20, and so on. So what that means is, let's just look at our graph. That means that the value 19 is going to happen halfway between a trough and a peak on this curvy part here. So we can use any cycle, let's say this first one, that's going to be a trough, that's a peak, and halfway between is the corresponding y-value when x is 19. Now we can check this in another way. If I start at 3 and I add on the period 4 a bunch of times, 3, 7, 11, 15, 19. So I'm going to put a little statement here. The y-value when x equals 19 is the same as the y-value when x is, and as I just said in the last, when I was pointing at the graph there, when x is 3. F at 3 is -1, and so f at 19 is also -1. So that's like a long explanation here. We're going to work on something similar. We're going to do 115 though, which this strategy is not going to work that well for. Counting up by 4s is kind of an irritating way to do this. So I'm going to give you a different strategy that we can use to find out what will this graph look like when we get to x equals 115 way to the right. And to do this, we'll look at how many cycles occur between our beginning 2 and this x value of 115. So we want to know the number of cycles on, we're going to call it an interval. Wow, I didn't even come close to spelling that right. Interval. So the number of cycles on the interval, we get that by taking the end of the interval, so the maximum x value, and we subtract the beginning value, so it'll be 115 minus 2. And we divide that by the size of a period, so it's the total distance from left to right, but divide by how many, or how wide each chunk is going to be. So in our case, that's 115 is the end value, subtract 2 for the beginning, and divide by the period, which is 4. So 115 minus 2, that's 113. We travel 113 divided by 4. Now that's not going to be a whole number. That's going to work out to a fraction. It'll be 28 and a quarter, 28.25. Oh, I'm sorry, I'm off the screen for you. So 28.25. So because the function is periodic, this 28 says how many times does it repeat exactly the same thing and start over. So really, only the 0.25 really matters. This tells us how far into a cycle the function will finish when we get to 115. So let me just write down some words to go along with that. So when x is 115, the function is in the same place, we're going to say, this is not technical language, as when it is 0.25 periods from the start. That's when x equals 2. We decided that was the start of the function. So what's a quarter of a period? Well, a period is 4, and a quarter of 4 is just 1. So let me just write that down. 0.25 times the period. That's 0.25 times 4, which is 1. Okay, so let's wrap this all up now. F of 115, the value we're trying to find, is the same as f of the beginning plus 0.25 times 4. How far into a cycle are we? How big is a cycle? That's how far past the beginning we are. So let's label this. This is the beginning x value. This is sort of the extra cycle fraction, or the portion of a cycle that we're into. And this is the size of a cycle, which is called the period. Okay, that's a long way to say f of 115 is the same as f of 3. And maybe I'll go back to our diagram again to find that out. F of 3. Look at that, we're at -1 again. Okay, let's try with a larger example, maybe a more complicated looking one. The function g of theta doesn't have an x, it uses an angle theta, has a domain of theta is any real number, and the range goes from -1 up to +3. There we go, from -1 to +3, and the domain units are in degrees. So this thing continues forever, it's periodic, and let me just label the axes here. That's the theta axis. This is quite normal for this part of our course, and that's y still. Okay, so there is our function, and this is a sinusoidal function. We're going to learn about this shortly. It goes up and down and up and down, and it just repeats perfectly forever. Maybe I'll just do a little bit of labeling on the scale. There's 300. That makes 1, 2, 3, 4. It looks like this is divided into chunks of 60. 60, 120, 180, 240, 300. There, that'll be a little easier for us to see, and there's 360 right there. Okay, let's stop there for now. Let's find the period of g of theta. That's our first step. Well, what we want to do is look for any really good point that we're sure about the value of. For example, we could use a peak, we could use a trough, or we could use something really nice like this point right here. But let's go ahead and use this peak right here. There's a peak at 60 degrees and 3. We go down and back up, and there's another peak at 300 degrees and 3. So let's use those points. I'm going to use 300 degrees and 3, and I'll use 60 degrees and 3. And that tells me that the period is, take the larger value and subtract the smaller value, the x values, or theta values here, and that's going to be 240 degrees. So this thing, every 240 degrees should repeat. So let's just check that out. Does that seem to work out? At the beginning we start here, so I would expect to be in the same place after 240 degrees. Okay, there's 240, it's in the same place. So 240 and another 240 is 480. Up, down, and up. Is that 480? Let me label a little bit more here. That would be 420, 60 more is 480. Yeah, sure enough, it looks like we're getting a nice cycle every 240 degrees. You can see it on the graph, and the easiest way is to pick two corresponding points that match in consecutive cycles. Okay, let's look at our questions now. What is the theta value, that's like an x value, of the next peak to the right? Well, we're going to need to look here, and there's a peak coming. So I can probably just count this right on the graph. Let me finish labeling, I suppose. That'll be 540, 660, 720, and then there'll be something else coming after that. Now, the peaks happen, let's look at our first cycle, 0, and then 60 after that is our first peak. We have this point here that matches this point. So we should be 60 degrees after this point to reach our peak. From 720, 60 more would be 780. So I can just write that down right here. The theta value is, I'm going to write down how I got it, 720 plus 60 degrees is 780 degrees. Once again, that's using a point that I can see on the graph and finding my way past it to the matching point using an earlier cycle for reference. So what is the theta value of the next trough to the right? We're going to do this slightly differently. I'm going to find a trough, this one right here. There's one at 660, and I'm going to add the period onto that value. So a little different approach. The theta value of the next trough is the last trough we had plus the period. So 660, that'll be 900 degrees. So let's just recap quickly then. You can use in this case I used a trough to find another trough. In the last one I could have used 540, this peak, and added on the period to find the next peak. Instead I used this point here and found that little difference by referencing an earlier cycle. Anything's fine here as long as you realize that you're ending up in some portion of a coming cycle. Well, and I just realized that my next question was to find out what is the y-value when theta is 900 degrees, but of course we just figured that out. Let's just skip that one and go on to this more challenging one. What is the value of the function, the y-value, when theta is 7,020 degrees? All right, well, that is really, really far to the right, and we are not going to count our way there quickly. So instead, we're going to use the same strategy that we used before to figure out how many cycles have passed. Now this function goes through the y-axis here, that is, it has 0 as part of its domain, and so we can, and it's even so nice that we can kind of look at this as a single cycle right there. In the previous example, our cycle didn't start at 0, but this one does, which is pretty cool. So what I would like to do is chop it up into 240 degree chunks. So 240, 480, 720, and so on. So to do that, I'm just going to divide the number we're looking for by the period. So this is going to be the number of cycles, which would be 7,020. Now, I could have had a minus the beginning, which was minus 0. I don't need to do that in this case. Divided by the period, which is 240 degrees. Grab my Casio FX300 ES Plus. Okay, 117 quarters, and as a decimal that's 29 and a quarter. So 29, I'm going to write it as a mixed number perhaps. 29 and a quarter. Once again, the 29 doesn't matter. 29 full cycles and then a quarter of a cycle. So this function, g at 7,020 degrees, is the same as the value of g at, if we start at the beginning, 0, and add on a quarter of a cycle. So 0 plus, I guess I'll write that down, 0 degrees plus a quarter of a cycle is 1/4 of 240 degrees. That's g of a quarter of 240 is 60 degrees. And I can just look at my graph now. It looks like we're at a peak, so that'll be 3. So at 7,020, that is a peak because it's the same as the function is at 60 degrees. Now if you want to double check this, you can see that 7,020, subtract that little 60 at the beginning, we get 6,960. If I divide by 240, I should get a perfect number of cycles. Let's take that, divide by 240. Sure enough, that's exactly 29 cycles as expected. So 720 is exactly 29 cycles away from 60, which is a peak. Okay, we have one more to do. What is the value of the function when theta is negative 780 degrees? Okay, well, that's going backwards here, so that would be negative 60, negative 120, negative 180, and so on. Well, the same strategy applies here. We can figure out how far back is it to go 780. So the number of cycles moving in that direction, if we want, we can use the negative version of this. Negative 780 divided by 240. We'll get a negative number, which means we're going to the left. Negative 780 divided by 240, negative 3 1/4. So negative 3 1/4 cycles. So that's to the left. So that means, since we're going like one full cycle, 2 full cycles, 3 full cycles, and a quarter of a cycle back, we're going to be the same as if we were at negative 60. So G at negative 780 degrees is the same as G at negative 60 degrees. For the same reason that this was a quarter of the way to the right, this is a quarter of the way to the left. I can just look at my graph now and see that that is a trough. And so that number will be at negative 1. Now if you don't like that whole negative business here, some negative number of cycles, being 1/4 of the way to the left is the same as being 3/4 of the way to the right. So 1, 2, 3/4 of the way to the right is also a trough, and so you can think about it that way instead. Okay, so I hope that is helpful. If you have any questions, of course, go ahead and ask. Thanks.